All right, here we go. So today we're going to learn a little bit about equilibrium. All right, we did some of this last year. We're going to cover about half what we did last year in a slightly more involved fashion. Yeah, so here we go. So we're going to do a lab on this, which I think will really help you guys get a better sense for it. For now, here's what you need to know about equilibrium. All right, we say that an object is in equilibrium if both the net force and the net torque on the object are zero. Okay, so basically, this means that the object is either not moving or the velocity is constant, and here it's either not rotating or rotating at a constant angular velocity. At this point, all of our objects are going to be, all we're going to focus on is this net force piece. Okay, we're going to focus just on ensuring that our net force is zero. Okay, so here's kind of the classic example. All right, so imagine this: you've got this 10-kilogram sign. It says "Eat at Joe's." All right, and it's being supported first of all by this cable here, cable number 3. Right, and then that cable has a joint, and it is pulled off this way and this way by cables 1 and 2. Okay, and we know that this thing is 10 kilograms. All right, and our goal is to figure out the tension in cable 1, cable 2, and cable 3. Okay, so and you can see you're given some angles here. Right, we're told that this angle here is 30 degrees, and this one is 45 degrees. Okay, so here's what we're going to do. Okay, so the first thing, let's deal with cable 3, all right? So the idea is we've got this 10-kilogram sign, all right? And there are only two forces acting on it, right? Gravity's pulling the sign down, so 10 times 9.8 gives us negative 98 newtons. And then cable 3 is holding it up, so that means the force from cable 3 has to ensure that our net force is 0, and therefore the force of cable 3 is just 98 newtons. Okay, so there's one of the three, okay? Now, figuring out what's going on with cables 1 and 2 is a little bit more involved. All right, so to do that, here's what we're going to do. For a moment, we're going to focus on making my smartboard work. There it goes. We're going to focus on this point right here. Okay, and the idea is that point right there has to have a net force of 0, right? Because that point is not moving, right? Okay, so let's identify the forces that are acting on it. Well, if the rope is pulling the sign up, then the sign must be pulling the rope down. So that means force 3, which we just figured out to be 98 newtons, that's got to be pulling the sign down, right? And don't forget that negative sign, okay? Now, there are also these other two forces. There's the yellow force 2 and the blue force 1. What I'm going to do is I'm going to find the components of those forces, or maybe not find them, but label them, all right? So force 2 is pulling off at some angle, you know, kind of off this way, right? So that means that it's got a horizontal component to it, and it's got a vertical component to it. All right. Similarly, force 1 is pulling this way with some horizontal force, and pulling this way with some vertical force. Okay? All right, and now what we know is this. We know that that knot there, that point on the rope, is not moving, either horizontally or vertically. Okay? And so what this results in is two equations. We know that our net force horizontally has to be 0, and we know that our net force vertically has got to be 0. Okay? So notice, we have two unknown forces, right? We don't know force 1 and we don't know force 2. Two unknowns, two equations. Okay? And so that's how we're going to solve this thing. All right? So what we probably want to do is take a quick second and come up with expressions for our x and y components in terms of F1 and F2, right? Because those are our unknowns. Okay? So my F1 looks like this. And this is 30 degrees, right? That means that here's my F1x, here's my F1y. So F1x is just going to be F1 times the cosine of 30. Oh, but it's a negative, right? And then similarly, F1y is going to be F1 times the sine of 30, right? Okay, and then we can repeat a similar process for F2 to discover that F2x is F2 times the cosine of 45, and F2y is F2 times the sine of 45, right? Just by doing vector components, okay? So, unfortunately, I need all of this information. Let me do this. I'm going to pause for 1 second. Okay, so all I did there was I just consolidated all of the information that we just came up with on one screen. Okay, so now that we've done that, let's see if we can't solve this mess. All right, so watch what's going to happen here. So this first equation, net force in the x direction equals 0. That is the same as saying that F1x plus F2x have got to add up to 0, right? And we know that F1x is negative F1 cosine of 30. And then F2x is F2 times the cosine of 45, right? That's got to add up to 0. Okay? So from there, we need to solve this thing for either F1 or F2. So arbitrarily, I'm going to add F1 cosine 30 to both sides and then solve for F2 to get this. Okay, a little bit of algebra. Dividing cosine of 30 by cosine of 45 gives us this. F2 ends up being about 1.22 times F1. And obviously this 1.22 is rounded. All right, so there we go. There's one equation. Right? That equation was derived from this. We knew that our net force horizontally had to be 0. All right? So now what I'm going to do is I'm going to focus on this guy. Okay? So net force vertically is 0. Net force vertically has to be 0. Well, that means that F1y plus F2y minus 98 newtons, or I guess plus negative 98 newtons, has got to be 0. Okay, so I'm going to move the 98 to both sides, and I'm going to substitute in my y equations here. So I get F1 sine of 30 plus F2 sine of 45 equals 98. Okay, and so what I can do now is I can take this guy here and substitute 1.22 F1 in for F2. So now I've got F1 sine of 30 equals, instead of F2, I'm going to write 1.22 F1 sine of 45 equals 98. Aha! Oh, shoot! This is supposed to be a plus sign here. Right? I just brought my plus sign down from up here. Okay, so simplify this, and you end up getting sine of 30 is a half, so this is 0.5 F1. Here, sine of 45 times 1.22 gives us 0.866 times F1 equals 98. Add like terms, you get 1.366 F1 equals 98 newtons. Divide, and you discover that F1 is 71.7 newtons. And then, now I can use this equation here, plug F1 back in, and find out that F2 is just 1.22 times that, and it gives you 87.5 newtons. Okay, so there we go. Let's put those numbers into our drawing then. So what we just discovered is that F1 is, like my drawing here, let's clean it up a little bit. So we just discovered that F1 is 71.7 newtons, and that F2 is 87.5 newtons, and then F3 was 98 newtons. So let's think about this for a minute. Why does this make sense? Why would F1 be a smaller force? So vertically, there's a lot going on here, right? Both of these forces have vertical components. So the vertical component here plus the vertical component here adds up to cancel out the 98 newtons. Okay, but they're not necessarily equal. All right, but what does have to be equal is your horizontal components, right? And so the idea is, because this cable here is closer to being horizontal, more of this 71 newtons goes into this horizontal component, right? Here, because less of your force is horizontal, you need more force this way to get just as much horizontal force as is provided by the 71 newtons. Okay? In other words, the horizontal component, these two horizontal components have to be equal to cancel each other out. Here, more of the 71 newtons is horizontal, right? A larger sort of percentage of it, right? Okay, so anyway, that's how you solve those. Two equations, two unknowns. Okay? There you go. Equilibrium.